On the 3rd of July 2025, a robotic telescope in Chile called Atlas caught a faint smear of light crawling across the southern sky. First it looked like nothing. Pixel. A rumor. Within hours, astronomers around the world understood they were looking at something that did not belong to our solar system at all. A visitor from interstellar space, only the third ever confirmed, and by far the strangest. They named it 3I/Atlas. And it was already moving too fast to be ours. While most comets drift lazily around the sun in long, familiar loops, this object was screaming through the solar system at more than 130,000 miles per hour, on a hyperbolic path that traced back not to any planet, not to any belt of icy debris in our own backyard, but to the depths between the stars. It had been traveling uninterrupted for longer than human civilization has existed, possibly for longer than our sun has existed. Some early estimates placed its journey at over 7 billion years, older than the solar system itself. A wanderer born around another star, flung out by gravity long before Earth had oceans, drifting through the dark for eons, and now, for a few fleeting months, passing close enough for us to see it. That alone would be enough to make headlines. But then the James Webb Space Telescope turned its enormous golden eye toward the object, and what it found made even seasoned astronomers pause. Webb doesn't see the world the way our eyes do. It sees an infrared, a wavelength that lets it peer through dust and gas, reading the chemical fingerprints of anything it studies. When it locked onto 3I/Atlas, it expected to find the usual mixture found in solar system comets: water, ice, carbon dioxide, maybe a trace of dust. What it actually found was a comet unlike any that had ever been catalogued. The coma, the glowing cloud of gas and dust surrounding the object's icy core, was saturated with carbon dioxide, in proportions far higher than astronomers had ever recorded in a comet before. In some of the data, CO2 outnumbered water by ratios that shouldn't be possible if this object had formed anywhere close to a sun-like star. Water ice sublimates, turn straight to gas, well before carbon dioxide does as an object warms. So a comet skewed this heavily toward carbon dioxide is telling us something about where it was born. Somewhere far colder, far darker, likely in the outer reaches of another star system, where temperatures never climbed high enough to boil away the CO2 ice trapped inside it. In other words, 3I/Atlas isn't just visiting from another star system. It's a frozen fragment of the outer edge of another star system, a place none of us will ever travel to, delivered to our doorstep intact for the first time in recorded history. And then there was the nickel. Spectral data revealed the unmistakable signature of nickel vapor streaming off the object, without the usual accompanying trace of iron that normally rides alongside it in solar system comets. On Earth, and in nearly every comet we've studied close to home, nickel and iron are chemically bound together, released in pairs when heat frees them from ice. But 3I/Atlas was releasing nickel largely on its own. Astronomers had only seen this strange, decoupled signature once before, in a peculiar class of interstellar adjacent objects, and no one has a fully settled explanation for how it happens. Some researchers point to unusual compounds like nickel tetracarbonyl, a molecule that can release nickel at much lower temperatures without needing iron along for the ride. If that's the answer, it means 3I/Atlas carries chemistry assembled under conditions that simply don't exist naturally in our solar system. Every new measurement made the object stranger. Its coma glowed with a peculiar blue-green tint in visible light, hinting at diatomic carbon and cyanide gas boiling gently off its surface even while it was still remarkably far from the sun. Behavior more aggressive, more active at greater distance than almost any comet we've observed. Most icy visitors stay quiet and frozen until they're close enough for solar heat to really go to work. 3I/Atlas was outgassing while still deep in the cold, as if something inside it were more volatile, more eager to escape than the ice we're used to. Then came the trajectory data, and with it, the moment the story shifted from remarkable to unsettling. Astronomers modeling the object's path discovered that its arrival lined up, with striking precision, with the plane in which the planets of our solar system orbit, the ecliptic plane. Statistically, an object entering from interstellar space on a truly random trajectory has only a small chance of aligning so closely with that plane. Yet 3I/Atlas came in almost exactly along it. Its closest approach to the Sun in late October of 2025 would carry it near the orbit of Mars, and its path would also bring it into proximity with Venus, Jupiter, and, closer than comfortable, Earth itself, though at a distance still safely measured in tens of millions of miles. For most scientists, this is almost certainly coincidence, or a signature of some subtle selection effect in how objects like this are detected. Space is vast, but orbital planes are not infinite in number, and interstellar objects have limited plausible corridors of approach shaped by galactic dynamics. Still, a small number of researchers, including at least one prominent astrophysicist known for provocative, high-profile hypotheses about interstellar visitors, raised the question publicly: what if this trajectory wasn't random at all? What if an object built to survey a solar system would choose exactly this kind of path? One that swings past several planets, gathering the maximum data without needing to expend fuel to change course. It's a minority view. Most astronomers studying 3I/Atlas say the data points overwhelmingly to a natural object, an ancient alien comet, not a machine. But the fact that the question was raised at all by credentialed scientists using real orbital mechanics is part of why this object gripped the public imagination the way it did. Because even in the most conservative interpretation, 3I/Atlas represents something we have never truly had before: a physical sample of the material that built another star system, arriving on our doorstep, studied in real time by the most powerful telescope humanity has ever built. As Webb continued watching, it also caught something that startled even the researchers running the observations. The object appeared to brighten unexpectedly as it approached its closest point to the Sun. A jump in brightness some scientists estimated as far larger than typical cometary activity alone could explain, at a moment in its journey when it should have simply been warming gradually, not surging. Comets can flare, certainly. Icy crusts crack, fresh volatile material is exposed to sunlight, and a burst of outgassing follows. But the abruptness and scale of this particular jump left theoretical models struggling to keep pace with the incoming numbers, and for a short while, telescopes across the globe redirected their attention toward the object almost simultaneously, each one trying to capture the moment before it faded. Ground-based observatories in Chile, Hawaii, and South Africa joined the effort. The Very Large Telescope, Gemini South, even amateur astronomers with backyard equipment managed to catch glimpses of a faint, elongated smudge moving steadily against the fixed stars, a visitor indifferent to the astonishment it was causing 67 million miles below. Estimates of its size shifted repeatedly as more data came in. Early guesses suggested a nucleus perhaps a few miles across, though the true dimensions remained difficult to pin down, obscured by the very cloud of gas and dust the object was shedding as it warmed. What we do know is this: whatever solid core lies at the center of that glowing halo has likely existed, largely unchanged, since before our own planet finished forming. It has drifted through light years of near absolute zero darkness, unlit by any star for most of its existence, a silent traveler carrying inside it the raw chemical memory of a stellar nursery none of us will ever see with our own eyes. And soon it will be gone. By late 2025 and into 2026, 3I/Atlas began its outbound journey, retracing a path away from the Sun and back toward the interstellar dark, never to return. Unlike a solar system comet on a predictable orbit, there will be no second pass, no follow-up mission decades from now. This was it, a single, narrow window in which humanity's instruments happened to be pointed in the right direction, at the right time, to catch a fragment of another star system as it passed silently through our own. It's worth sitting with that for a moment. In the entire multi-billion-year history of Earth, in the few hundred years we've had telescopes capable of catching something like this, and in the mere handful of years we've had an instrument as powerful as the James Webb Space Telescope, all of that had to align almost impossibly for us to witness this. Two interstellar objects came before it. Oumuamua in 2017, tumbling and strange, gone before we could properly study it. Borisov in 2019, more comet-like, but still limited by the telescopes of its era. And now 3I/Atlas, arriving in an age when we finally have the tools to really look, infrared eyes powerful enough to read the chemistry of a rock born around another sun, light years away and billions of years in the past. What Webb has shown us is not proof of anything artificial, not confirmation of visitors, not a signal from another civilization. What it has shown us is something quieter, and in its own way just as extraordinary: that the universe is not sealed off from us. Material from other star systems is not locked away forever behind impossible distances. Sometimes, Rarely, it comes to us, tumbling in from the dark, carrying chemistry we've never seen up close, offering a fleeting chance to study the building blocks of a solar system that isn't our own. 3I/Atlas will fade from our skies, sliding back out into the space between stars, carrying its ancient ice and its unanswered questions with it. We will likely never see it again. But for a few months, across observatories on nearly every continent, humanity turned its collective gaze toward a single point of light and asked the oldest question there is: what else is out there? We didn't get a final answer. Not really. What we got was something rarer, proof that the question itself is answerable. That somewhere other stars are forming other worlds, shedding fragments of ice and rock and strange, decoupled metal into the void, and that every few decades, one of those fragments finds its way to us. Silent, ancient, indifferent to our astonishment. And long after 3I/Atlas has vanished back into darkness, the data it left behind will still be here, in spectra and light curves and orbital calculations, quietly waiting for the next generation of scientists to look again, and wonder again, at just how much of the universe still remains unseen, drifting somewhere out past the edge of everything we know.